Okay, so today we are going to learn about torque finally. So I've mentioned this concept a couple times. And again, if you are into cars or mechanics just in general, you probably have heard of this concept of torque before. But before we define it, let's look at an example of it. So you approach a door that is pushed to open. Where are you going to push it? Well, you're probably going to push it right at the edge of where it opens, right? If the door's hinge is here and this is the edge of the door, you're going to want to push it right there, right? Now, instead, if you push the door 10 centimeters from its hinge, so here's where the hinge is, and you decide instead to push it right here, even though the door goes all the way out here, is that going to be easier or more difficult to open? Go ahead and try it if you're not sure. It's a little bit more difficult, actually. We automatically go to the edge of the door to push because it's going to be easier. If we push really close to the hinge, it's more difficult to push. Now, what happens also if you push the door on the hinge? If here's the hinge and I'm just trying to push with all my force on the hinge of the door, what's going to happen? Nothing. The door's not going to open, right? This is the concept of torque. If I generate more torque, I have an easier motion. We can say it that way. I need to use less force, and we'll talk about that in just a bit because the torque formula, it looks like it's not a lowercase t, it's a small capital T, pronounced tau. This formula is R times F, radius times force. However, we have to be very careful with this. R specifically means the distance from the point where the force is applied to the rotation axis. So I'm talking about the door. The rotation axis is the hinge. And wherever I push, R is the distance between those two, between the rotation and where I'm applying that force. Now, F is very specific. And this is true in any case, back when we were talking about forces a lot. The F that we're talking about specifically has to be in the direction of motion. In this case, we're talking about the force component applied perpendicular to the rotating vector. This sounds really fancy, but it means if I have a door, we're talking about the component that is straight onto it. If I push the door at an angle, we need the component perpendicular to it. So we'll talk about that later. You'll see it a bit more in a picture what I mean by that. This perpendicular is technically in the direction of motion, right? If here's my door and I'm pushing straight on, I should say, that's perpendicular, right? That's a right angle. But there we go. This is like, how can I do my hands? So here's my door. This is the force component perpendicular. Obviously, as the door opens, I start to kind of swing up, but I'm keeping that force perpendicular to my door versus if I push the door like this, we're looking at the perpendicular component, right? We should know this makes a right triangle and we can find the perpendicular component there. So the units for this. Now again, guys, by now we should know how to figure out the units for something. If this formula is radius times force, that's what the units are going to be based on. Radius is measured in meters and force is measured in newtons. And so we flip it just because the newtons is a bigger deal. We call this a Newton meter. So this is basically how much force per meter, meaning distance from the center of rotation, we're applying on something. Let's talk about, from here, what this formula means and how we can kind of modify it and work with it. So if this is our formula, tau, torque, equals radius times force, perpendicular to the direction of motion, perpendicular to the, the rotating object, excuse me. If we apply the force further from the rotation axis, this means a larger R, right? What do we think is going to happen to our torque? We're going to have more torque. That means we have an easier time rotating something, right? Torque is this concept of being able to rotate something easier. We can think about it like that. If you apply the force perpendicular, so this again means straight on. perpendicular to the rotation vector. If my arm is the rotation vector, meaning the thing that's doing the rotating, if I apply it straight on, this is going to mean more torque as well, because my component is strictly a perpendicular component. Versus if I don't apply it straight on, my perpendicular component is going to be smaller. So straight on, this also means more torque. This is why when we come up to a door to push, we push straight on. We don't like push it at an angle. That's kind of weird, yeah? Now, last thing, if you apply the force parallel to the body rotation vector, what this means is sideways. If you can imagine, a door is kind of open, but to keep pushing it open, instead, you push where the lock is at, and you're like trying to push it that way, it's not going to move. There's no torque, yeah? So again, if this is my door swinging open, that would be like pushing right here. That's parallel to the body that's rotating. It's not going to move, right? I need to push this way, yeah, for it to move. So if I'm pushing parallel, this is again parallel to the body, you're going to have no torque. It's not going to move, yeah? You are going to be unable to move it. So we have to produce some torque in order to get the body to move and to rotate. So looking at these two situations here, this is our axis. So if you can imagine, it's like the hinge of the door. That's what it's rotating on. Where'd my F go? There we go. So this is the same force. It is the same magnitude force. And this is the length of our rotating body. In which situation will more torque be generated? Again, it's the exact same force being applied here in respect to our axis versus being applied here in respect to our axis. Which do you think is going to generate more torque? A is definitely going to generate more torque because it is further away from that axis of rotation. Whoa, where did my stuff go? There we go. Okay. A is going to generate more torque because, again, this R is greater than this one. That's the distance from the axis of rotation over to where the force is applied. Doesn't necessarily matter the length of the object. I mean, technically it does, but we are focusing on, right now at least, this little distance right here. Now look at this situation now. So now we have these forces being applied the same distance away at the very edge of the rotating body. But here my force is being applied straight on versus I'm kind of approaching the object and pushing it at an angle. Which one is going to produce more torque? D is going to produce more torque because, again, all of my force is straight on to technically the direction of motion. Again, obviously, as this opens, the motion actually, it rotates. But here, again, this is the perpendicular. This is the F that we would use in the formula, right? Again, we have to keep that straight. If we're looking at that formula, it doesn't just mean the force. It means the force perpendicular to the object. So we would need to find this component, and it would be less than the general force overall. So this situation would produce less torque. This situation produces more torque. Again, I highly recommend, if you're like, I think I kind of understand it, go up to a door and try it, right? Try pushing the door straight on with your hand flat. Try kind of angling your body and pushing it at an angle. I know that seems a little bit weird, but pushing like here versus straight on to the door. Try pushing it close to the hinge and further away from the hinge and see what's easier and what's harder. If it's easier, that means you produced more torque. So let's do one more little concept here, and then we're going to try some examples. So we can apply Newton's second law to this concept of torque, because again, torque is basically the force we're applying to a rotating object. Oh man, oh well. Okay, so going back to Newton's second law, this says a net force results in the acceleration of an object. This was the basics, right? So Newton's second law gave us the formula net force equals ma, right? This is Newton's second law. Now, when we have rotational motion, though, we don't talk just about the force. We actually have the torque, right? That we're talking about here. So the torque net is going to equal I alpha. Do you remember what these variables are? What did I stand for? This was rotational inertia, and there's the formula again. I meant to have it as a click to enter, but whatever. There's our formula for rotational inertia. Remember, rotational inertia refers to how difficult it is to move an object, to rotate an object, based on its mass and based on that distance from its axis, yeah? And then what was alpha? Angular acceleration. So we do still have acceleration here. Instead of F equals ma, we have torque equals IA, basically alpha, right? So we're going to use this in the second question that we do. We'll keep this in mind. If we're dealing with forces and we want to find an acceleration, we're actually going to be using this concept instead of an angular kinematic formula like the velocity formula or position. We would actually instead use this. So let's go ahead and look at this first example here. So this one says, what is the torque about your shoulder axis if you hold a 10-kilogram barbell in one hand at arm's length and at shoulder height? Now, what we are looking at is not the net torque. Again, a net torque would result in an acceleration. We don't care about that right now. Torque can still be generated even if there is no motion, because if you're holding a barbell out, you are actually exerting upward torque in the opposite direction to keep the barbell steady. That barbell does exert torque on you, but you are actually exerting it in the opposite direction to keep it up so your arm doesn't swing down. Yeah. So we are ignoring that you are technically exerting an upward force opposite. We are just looking at the one force and the one torque versus the net torque. We're not looking there yet. So torque is tau equals RF. Now let's look at this picture again. You are here. I'm going to draw a little picture. Why not? You are here holding a barbell. What we need to keep in mind is the angle. The barbell's weight causes a force, right? Straight downwards. So if you're holding your arm out, the force of the barbell is perpendicular to your arm. So what this means is the force that it applies is this force. We don't have to find a separate component, because again, the weight of the barbell is acting perpendicular to your arm. If instead the arm came up and wasn't at shoulder height, well, now the weight of that barbell is acting straight down, and that is not perpendicular to your arm. We would have to find the perpendicular component. So in this case, though, it is perpendicular, so this force is the force we need. Now you have to keep in mind here, we have your hand is 75 centimeters from your shoulders. So how much meters is that? 0.75. So this is the R, 0.75 meters. Now, what's going to be the force, though? Again, what we just said was the weight of that barbell is the force acting down. What is the weight of that barbell? It's not 10 kilograms. Remember, how do we calculate weight? Your weight is the force of gravity. So this is the mass, but if you can recall, weight, sometimes we forget this, is not the same thing of mass. Weight is your force of gravity that you generate, we could say, yeah? So that's going to be mass times gravity. So in this case, the force is mass times gravity. This is going to be 10 times 10. That's 10 kilograms, and that's 10 meters per second squared for gravity. So we have here, should just be 75, right? 75 Newton meters. And that is how much torque is being generated. Again, to keep that barbell steady, you are generating an upwards torque yourself through your muscles. So the net torque would be 0. But if we're just looking at the torque of just the barbell, that's what's being generated here. How much force pulling down and the distance from your arm. If you had a longer arm, that would be more difficult, right? Somebody who has a very short arm, it's not as hard, it's kind of weird. It's not as hard for them to keep that barbell steady versus if you have a very long arm, it's going to be more difficult because this R is going to be greater. You're holding it further away from your body. That's why it's hard to do this than to hold the barbell in right here. Very close to the center of your body versus out and away. Okay, let's look at this last one here. So we're talking about a wrench now. So this is actually what's called a torque wrench because it uses the concept of torque to tighten bolts, or in this case, a nut on a bolt, which makes it a lot easier versus having to use your fingers. Yeah, longer wrenches are easier to work with and can generate more torque because that R is going to be longer. So this is how the concept of these wrenches work. The longer the wrench, the more torque it generates. So the wrench is 25 centimeters long from where you're holding it and applying the force, right? Now, at that 25 centimeters, a force of 120 newtons is applied with a slight angle of 25 degrees. So you can see this is where the force is applied. So you can kind of imagine your wrist being there, pushing it at an angle. This is the force applied. Notice it is not perpendicular to the object. So we're gonna have to keep that in mind when we calculate the torque. So tau equals RF. However, the F we need is perpendicular to the object. So I want you to take a moment, hopefully you can see this triangle here. This is the 20 degrees right there. I'm gonna go ahead and actually pull that triangle off. We got one more example down here. Okay, so what we have in that little triangle right there is that this is the force applied at an angle of 20 degrees. We want to find the force perpendicular to the object. Go ahead and find, using a little triangle right here, what is the force perpendicular to the object? Well, that's going to be that one, right? We can call it Fy if you want to, in keeping with our standards. Yeah, that's like the Y direction. So that should be cosine, right? I'm going to go ahead and do the whole thing just so we can see it. We got cosine 20 equals the force that we want over 120. So the force that we're going to use in our formula is going to be 120 cosine 20. So it's going to be 112.76. So this is the force we have to use, the one perpendicular. Notice this is a right angle right here as well. Here's my object. Here's the force component that I want. So tau equals, let's go back up here. We need R, 25 centimeters, careful there. That needs to be 0.25 meters. Times our force component is 112.76. Excuse me for my terrible handwriting. So this is going to be the torque we are generating. We've got 28.19. And again, this is Newton meters, we can say. Newton meters. That is the torque we have generated. So again, keeping in mind that if they applied that torque directly straight on, if that force of 120 newtons was applied totally perpendicular, they would generate more torque. As well as if they had a longer wrench, we would generate more torque. So just keep that concept in mind. So this last thing here is based off of Newton's second law, and here's how we know. Again, it says, what is the angular acceleration of the wrench? you might go into this thinking, oh, I need to use a kinematic equation to solve for alpha. But we're dealing with forces here, right? We have a force applied and a rotational inertia. So this is using Newton's second law as it applies to rotational motion. Take a moment to copy that law down from the slide we looked at earlier. So this was the fact that torque net, we can call it tau or you can just say torque. Torque net equals the rotational inertia times alpha. So if we're trying to find alpha, if we know the torque net and we know the rotational inertia, we can find this acceleration. So take a moment. We know the torque. We know the rotational inertia. Go ahead and find alpha. Okay, so we are going to assume, I kind of made this assumption, that this is the net torque. Again, there's friction forces involved, which cause torque in the opposite direction. We're going to ignore that for right now. So the torque is 28.19. The rotational inertia based on the mass of this, as well as the length of it, is 0.0625. We are trying to find alpha. So they already calculated the rotational inertia for us. If they gave us the mass of this object, we would need to calculate that ourselves. Because again, this is mass times the length squared. Careful guys, real quick, I wanna make this note. This R refers to the length of the object. Sometimes you will see that as L, versus this R refers to where the force is applied. That can be different. Notice that they did not give us the full length of the object here. They gave us up to the handle, which is where the force was applied. So be careful when dealing with rotational inertia, that's actually the length of the object versus here is referring to the distance where the force is applied. But again, because they already calculated it for us, we're good. We don't have to worry about that. We just got to plug this in our calculator. We got 28.19 divided by 0.0625. We have 451.04. This is again going to be radians per second squared. So this generates, again, a really quick acceleration that's actually a decent amount of torque. Obviously, you're not going very far, right? A wrench, you're just kind of going back and forth. But the acceleration is actually very quick because you're generating a decent amount of torque to get that moved around. Okay, so we're going to practice a couple more extra problems with this before we move into more difficult concepts dealing with torque.